So you want me to?
Okay, well, let me introduce Martin Oberlack from Darmstadt. And he'll be talking about high order moment scaling laws in wall bounded shear flows and beyond. And Martin will be here next week in person. He's arriving Sunday, apparently. So if you have any questions you really want to talk to Oberlack, he will be here. So, okay, Martin, all yours.
Okay, Rick, thank you very much. Thank you all the organizers for inviting me here to this talk. I feel very much honored to give the talk here. Let me just briefly mention my co-worker, which is Sergio Hoyas from Valencia, and two PhD students of us, that is Stefan de Krauberger from Darmstadt, and Francesco also from Valencia, and another student, a bachelor student from our group here. Well, what we're going to talk about today is essentially a very classical subject in turbulence, and that is, essentially scaling behavior in wall-bounded flows. And classically, of course, if we say look at a shear flow close to a wall, a parallel shear flow, and from many textbooks, of course, we know the famous equation that was derived by von Karman and Pruntel, and that is this one here, is essentially based on dimensional reasoning. And then if you integrate that, introduce the plus variables, you get the famous log law. And then what happens, of course, is comparing that to data. This is, for example, here, Ivan's your data. There is an extremely good fit to the data with this semi-empirical law. So I would say there's very little connection to Navier-Stokes whatsoever, and try to convince you that we can at least achieve a little bit of that. So the motivation here is to derive high moment scaling laws, also including PDF. At the very end, I will talk a little about scaling behavior of PDFs, and we will focus on log region, essentially the near wall part here. I always circle the region, and then also we look at the core deficit region that is in the center of the channel. For that, we actually conducted a very large DNS at Reynolds tau of 10,000. The reason was that we wanted to see very clear scaling, and I think we achieved to a certain extent. For those who actually listened to my talk, probably know a few of the coming slides, and that is the idea of a symmetry. So the concept of symmetries, well, it goes back to mathematicians like Sophus Lee and others, Felix Klein, and it was kind of learned from MVJ geometry. I mean, if you have a cylinder here, you rotate the cylinder, and that it looks the same, it means essentially that this is a symmetric object. Now, mathematicians have introduced the same concept to equations or differential equations. So suppose you have an arbitrary differential equation here, and you're in the position to derive a transformation as such to a new set of variables here, x star and u star. And now if you take this transformation, plug it back into the equation, you get the same equation. So what we have is kind of a form invariant transformation, and this transformation is a symmetry or symmetry transformation or Lie group. That is, so to say, the basic concept here. Let me just give you a simple example. That is the one-day heat equation. And for most of these equations, symmetries can be guessed. For example, scaling of space and time. For example, look here at scaling of space. That is x star. This is the factor here. And scaling of time with the same factor squared. Independent of that, you do have a scaling of time, of temperature, and that refers here to the A2. Now, if you take this, what we call the two-parameter group, into the heat equation, and what we observe, of course, exactly what we, according to the definition, that these two factors here cancel out, and what we have is apparently a scaling symmetry or two-parameter scaling symmetry. A second concept we need is what is called an invariant. Now, we are able to construct quantities that are also invariant. So, for example, this x tilde here or the t tilde here. So let's start with the x tilde, that is just x over square root of t. If you take now the transformation, plug it back in here, of course, this exponential factor drops out. You get something that has the same form, and apparently that is now what we call x tilde, that is an invariant. Something similar can be done actually here for the temperature. You can rescale with time into a little more complex fashion and do the same thing. You observe that this is an invariant. The next concept we need is what we call an invariant solution. That is what actually I'm trying to convince you later, that we can construct invariant solutions for equations that come from Navier-Stokes. And essentially what I'm showing here is this invariance. Now, if you take these invariants, put them into the heat equation, you find something what we all know, that is a similarity reduction, or just a group invariant solution. That means now, of course, this PDE now goes to ODE that can be solved in terms of special functions. The final concept that we need is here what is called symmetry breaking. Suppose that you want to look at the heat transfer on, say, on a rod, and you put a temperature here while the rest of the rod is insulated. Now that means at the point x equals 0, you have a fixed temperature. Now, if you take these scaling groups we had before, put them into the boundary condition, what we observe is that this quantity here, the A1, still remains undetermined, while this A2 here apparently has to put to 0, otherwise it would not be a symmetry of the boundary conditions, because otherwise the equations here at the boundary would be different. So T naught, so to say, we call symmetry breaking. What do we know in terms of symmetry of Navier-Stokes? Now let's get back to fluid mechanics. So essentially all of the symmetries are, I think, known. And what we need today is essentially two scaling symmetries. And of course, they are only valid in the limit of large Reynolds number. We may discuss that later. So we have scaling of space. Here it is A as X, scaling of space. Of course, it means also scaling of velocity and pressure. And we might also introduce scaling of time. That means the inverse here and the velocity, and also in terms of the pressure. Of course, there's Galilean group, rotation group, and all that. That is not relevant. What we know, however, and that is important, all these symmetries transfer to all the statistical equations that we know of. Now, let me switch to the statistical description of turbulence. That is a chart that was developed by Marta Wacławczyk some years ago. I really like it. And what I'm showing here is essentially on this chart, here's a number of points. Here is the order of the statistics.
Please, question, Martin.
Yep, please.
Go back to the Navier-Stokes things.
Sure.
So these symmetries are beautiful and nice, but you have in bounded domains, they break, correct?
That's true.
Okay, thanks.
Well, not necessarily. It depends.
I'm following, that's all.
Excuse me?
I'm just telling you, I just wanted to follow, that's all. Thank you.
Yeah, sure. Okay, so just to briefly just go to the ways we describe turbulence statistics. So as I said, this is the number of points. This is the order of the statistics. For example, eddy viscosity models are down here. So this is just 1 point. Reynolds stress models are up here, or 2-point models are up here. So now, if we look at just a multi-point approach, that of course means we, so to say, expand at the same time the number of points and the order of statistics. Quite different actually is the PDF approach, because here we immediately, once we have the PDF, of course, we have all orders of moments. And then that of course goes on that we go to further higher models of multi-point. What I will do for the rest of the talk, I will focus pretty much on that one here, to the multi-point moment equations, and at the very end I will briefly show you some very recent results, that is invariant solutions for the Lundgren equations. Just a quick word on the notation in turbulence. So the capital U and capital P are essentially instantaneous values decomposed into the mean value of U bar, and the little u here is the fluctuations, and the same for the P. And what we do is, and that is now kind of different, we define two different sets of correlations. Let me start with the classical one. That is just the correlation between fluctuating velocities here. The little u, that is what we call the R approach, the classical notation. And further, we have this what we call the H approach. That means we correlate the instantaneous velocities between the capital U's here. Of this one here, the upper one, of course, reduces to the Renner stress tensor if R is going to 0. Well, the interesting thing, I think, was the H approach, and that, of course, was the starting point of most of what we will show later, is the following. So if you just have Navier-Stokes equation here, incompressible, now if we multiply velocities, instantaneous velocities at different points into that equation, do the usual averaging process, we get this following equation. Of course, down here, you find the definition of these moments here. So this n here, n plus 1, is, so to say, the order of the moment. Two things about this equation. The first of all is it's a conservation law. This equation is in conserved form. Of course, it comes from quantum conservation, but still it's a conserved equation. Second, and that is important, it's a linear equation. It's infinite dimensional. We have this infinite set of equations. However, it's linear. Still, if you chop the equation at some point, of course, it's an unclosed equation. I mean, here, say, you have the tensor order n plus 1, and this term, which comes from the convective term, of course, is tensor order n plus 2. So this is what we will be using later on. However, I would like to contrast that with the classical notation. The classical notation here is based on the fluctuations, and you can do the same thing. You can write down an equation. I'm not going to talk about details. However, it's a very complicated equation. It has coupling among all of them, and it's not in conserved form. It's nonlinear. Here we have nonlinear terms here, there, and there. So it's infinite dimension, but it's nonlinear and has coupling of among all terms. Quite clear. These two approaches are fully equivalent mathematically. However, the first one was based on the H is much more easy. Here, just the usual way how things are coupled or related. I would say this H1 here, that was the first index here, is just the mean velocity. This second tensor here, this H of second order, is of course this classical plus the mean velocities squared and so on. So for the rest of the talk, most of the cases, I will focus on this H approach. Further, because at the very end, I will briefly mention the PDF. Of course, mathematically, it's much more sound to derive the moment equations based on the PDF. And that is, of course, called classically done. I mean, here, that is the probability density function here. That is the first moment here. That is the second moment, also multi-point here. And of course, you can do that to any arbitrary order. The PDF itself, of course, is based on a famous equation. That is the Lundgren equation, or Lundgren-Monin-Novikov equation. And it's also a linear equation. It's a linear equation. It's unclosed. So here we have the unsteady term, convective term. Here, that is the pressure term. Of course, it's a non-local term. Here you see that this is order n plus 1. And also the viscous term, of course, is order n plus 1, but still it's a linear, but now an integral differential equation. So it's all linear, but still infinite dimensional. Okay, now let's look at turbulence and symmetries. Well, let's go back to this H equation. Remember that this was based on these instantaneous velocities. And if you look at the equation, as I said earlier, it's a linear equation. That means, and now try to remember what I showed you earlier in terms of the heat equation. Because it's a linear equation, you can rescale all the moments with the same factor. That is what I wrote down here. So we call that ASS, that is well for scaling, but statistical. Same here for this pressure term. And that, of course, means that any moment here scales the same. That is important. Already in 2014, Marta Wardlowski showed that this has something to do with intermittency, and I show that in a minute. That is actually here. So this is, again, the moment transformation, the moment symmetry. It's a statistical quantity. It's not emitted by Navier-Stokes equation, but by any of the moment approaches, not by any of the statistical approaches. And what we showed, or what she showed at the time, was that you can transfer this moment symmetry into a symmetry of the PDF. And that I would like to just focus a minute, So suppose this is, so to say, the original PDF. What you have to do is here, you have to add delta function. Here's delta and there's a delta. And what you recognized at the time was, if you have a signal that, so to say, as, so to say, a classical, say, broadband PDF, what if you add delta function, that means you have a signal of that form. That means you have a turbulent signal, and then you have, so to say, a constant here, and you have a turbulent signal. So essentially, the PDF is of that form. That means, so to say, a classical PDF plus a delta. And that is why we were thinking that this is kind of a measure of intermittency. The way to get from here to there is not trivial. You have to go through characteristic functions, our characteristic functionals. I'm not going to explain that here. A second symmetry that is also important here, that is due to the fact that this equation is in conservative form. That means all of the terms are under derivatives. That means you can add a constant to all of them. In fact, also the heat equation has this property. You can add an arbitrary constant. And also this one here, you can actually interpret these things. In fact, this quantity here, this is very important, for example, for the log law. I'll show that in a minute. Here we call that shape symmetry or non-Gaussianity. And if you do that, if you take this symmetry here, that is, so to say, a shift in the moments, Marta showed that this, so to say, gives rise to a PDF symmetry of this form. Maybe just focus on that one here. So this function here, psi here, has to actually obey a certain side condition. And if you just do a little plotting here, suppose that it's your original PDF, you can add, so to say, this psi here. Of course, that integral has to be 0. And you get something that, so to say, gives you something that is definitely non-Gaussian. And that is important for things like skewness, flatness, etc., etc. Okay, now let's move on to data. Let me first show you a little bit of the data that that we did for the DNS with especially Sergio Hoyos. It's a pure Poisson channel flow pressure driven here at Reynolds tau 10 to the 4. The code is the classical code LISO that I think to some part was developed by Javier and also was used in that paper 2006 of Hoyos and Jimenez. It's Fourier in X1 and X3, compact difference in X2, and Runge took a time stepper. Computations were done mostly at Supermok in Munich. And that is the geometry here, essentially 2H classically. The box is relatively short, I come to that, and also the width is not extremely large. Here, just a quick comparison to classical DNS. That is the one from Hoyos and Jimenez in 2006. That is, I forgot actually, this is Lee and Moser from 2015, and this is the last one here is our one that was also published here in PRF recently. The numbers are slightly more coarse, but in the similar order of magnitude as the other ones. I think what the biggest difference is here actually that our box is smaller. That means, however, that we have to do longer calculations in order to get good statistics. The other things that we're going to compare to later is pipe flow experiments that come from two different facilities. The one is here, the Sanford International Corporation Long Pipe Experiment, Cyclope in Bologna. And the other one is from the Superpipe facility at Princeton. Reynolds numbers here are from 2000 until 94,000. So there's this enormous width in the Superpipe. And they were done here from the group of Joe Klavicki. Here, the Cyclope 2 is from around the group of Talamelli. And of course, here that has its origin, I think, from Lex Smith's group. Okay, now let me go to, so to say, the scaling laws that we can derive. So what we'll be looking at is the center region and the near wall region, and the same thing here for the pipe. This is, so to say, the center region, and this is the near wall region. and in the pipe flow. Scaling laws look very different. Look very similar actually. So there's so let me focus here a little bit on this a little bit more complicated slide here. So what we look at, because of the geometry, we essentially have a mean velocity that only depends on the wall distance. Of course, all higher moments, 1-point moments, also only depend on x2. That is, of course, the wall distance here. What are the symmetries we're going to use? Remember, this A as x was scaling of space. That also appears here. We also have scaling of time. Of course, it's in a statistically steady process, so we have put that in brackets here. That this is A as t here. And most important, we do have two statistical symmetries. That is A as s, so scaling of statistics form. And now remember what we had before, what we saw before, because the H equation is linear, then this A as s appears the same for all moments. So it appears here for the mean velocity, here's the second moment, and of course here, it's the nth moment is the same, still the same. For the dimensional scaling, of course, things are different. Here we just have, so to say, this factor here. For the second moment, we have the factor of 2. And to the nth moment, we have this scaling behavior here. The second important quantity here is this statistical symmetry that allows you for a shift. In fact, in the early days, in around the late 90s and the 2000s, I was misinterpreting that as Galilean invariance, but it's not Galilean invariance. That also appears to be holding true for the higher moments. Well, that is just a shift here in the coordinate system, not so important. Now, what we have to do is really a major jump now, and what we essentially having here is the invariance condition for scaling laws of the moment equations whenever things are, so to say, a fully parallel shift law. And this equation has quite some similarity. Remember the Prandtl von Karman equation. So if you take this quantity to be 0, suppose this factor here is 0, we exactly have this equation that is derived at the time in the 30s by Prandtl and von Karman. And you see later why that is important here. This quantity here, you need that. That is an important symmetry. It's a statistical symmetry. If that is 0, of course, everything breaks down. Now, what we are able now to do is we can write down this invariance condition that allows to construct similarity solutions. Remember what we did for the heat equation. So any solution to this set of equation allows you what we call symmetry reduction or invariant solution.
Oh, sorry, Martin.
Sure.
You explain, I'm sorry, my ignorance. The first equation, once again, how you get the first equation? P1,
yeah, that is sorry, that will probably not be able to show that in a few minutes, not even an hour, because what you need really is the whole concept of infinitesimal transformation, and the whole Lie group theory is based on this infinitesimal transformation, but that is not something that you can really introduce, so to say, very quickly in an hour session or so. So you just have to believe me that once you have this transformation, you can also construct what we call this infinitesimal form. And in this infinitesimal form, you can actually very easily construct these type of equations that allows you for similarity solutions. I may quickly go back to the heat equation. I didn't mention that, but this one here. I didn't say that. But what we have here on the left-hand side is an infinitesimal form, exactly this one here. That is, so to say, and here now that is what we call invariant surface condition, and in the lower part here, these are what is called the infinitesimal forms of the transformation. So yeah, it's kind of bad, but you have to believe me that this is a rigorous way to get to these equations here, and then once you have that, you can show that this is an invariant or a similarity type of solution.
So
I'm not sure. Is that-
Direct do with your moment equation, is that correct?
Excuse me?
That first equation is directly related to your first, the momentum equation H. Okay.
Yeah. I'm sorry, I should have said that. Because the H is essentially multi-point, what I'm going to do here now is only 1 point. So I'm just looking at the mean velocity, and this is the H, but just 1 point. So this is just the nth moment of U.
Martin, since you've been interrupted, can I ask a question too? So why are you pursuing an invariant solution under this infinitesimal operator?
Why I'm doing that?
Yeah. What's the rationale? Are you sort of looking for one special solution? Because normally when you have a transformation, it means, if I have one equation, I can move to a whole series of solutions.
Well, the reason for the why people, or why I'm using this infinitesimal form is essentially because the ease of use, I would say. I'm not sure, I understand that this is for an outsider who not familiar with this concept, it's not easy to understand, but the basic thing in group theory is that once you have, transformations, and you write them in infinitesimal form, these transformations in infinitesimal form can, they're what we call their linear vector space. So they can just linearly be combined. And that is essentially what I'm doing here.
It's not my question. It's not my question. The question is, why are you looking for something which is invariant under these transformations?
I see. Well, the point is, but the rationale here is saying scaling laws are invariant solutions. So invariant solutions are special solutions, that's for sure. However, we do know in turbulence in particular that turbulence likes invariant solutions. I mean, many of them have been found without group theory for many flows. So the rationale here is more or less similar, saying we want to show that these solutions, these invariant solutions, are in fact visible in turbulence.
Well, if they weren't the invariant solutions, there'd be multiple ones. So it's the other way of phrasing your question.
Right. So are we looking for uniqueness? A unique special solution?
That's a good point. The uniqueness is something that you have to ask other people.
Okay. Thank you.
Yeah. Well, but one more point. I mean, it was good that you're asking. I mean, the machinery allows you, in fact, to construct these things to an arbitrary order, I would say. That is probably the nice part, or part of it, I would say. Let me just move on here. So what we look at first is the near wall region. And I think one of the key ideas of Brundtland and von Karman was that they were just defining this u tau that we all know that is the friction velocity, and that is a quantity, and that is, I think that is the very brilliant idea that this quantity is symmetry breaking. Now, if you do so, suppose u tau, we assume that u tau is symmetry breaking. That means we can no longer scale the mean velocity. So this factor here in the exponent is 0. And now if we use that here, we exactly get what Brundtland and von Karman wrote down. I mean, if you just solve that, you get the classical log law. And of course, that is a little bit more slightly more general, but other people derived that too. Further, if you use this fact here, we are in the position to also write down the higher moments. And that is in fact the power law. And interesting enough, the only parameter that appears here is the little omega. So once you know omega for the second moment, say this is n over larger than 2, you have it for all of the higher moments. I come back to the Cn and the Bn in a minute. So let's compare that to data. So we just gathered here all the DNS data that were available, I mean, at higher Reynolds number. So this is the Hoyos Jimenez and so on. So the black curve here is our recent DNS, and we believe we see a reasonable good log law between, say, maybe 300 or so until 2.5 or 3,000, whatever you like. I think we go up to 2,500. Numbers are pretty much close to what have been observed earlier, but we believe here one can see probably the first time in the DNS a really log region. Now what we're plotting here is exactly, or the comparison here is with this higher moments here. So this is the DNS here. So this is the second, the third, the fourth, the fifth, the sixth moment. And what we do is we just fix, so to say, the omega for the second moment here, and then we just check with the data, and the black lines are essentially the theory. The symbols here are the DNS, and you can see that works pretty well actually. What we also did is what we call this indicator plot. This is, so to say, indicator plot for the log region. Forget about that, that's not so important. So this is the indicator plot for this power law. So if you just compute these numbers here from the DNS, the theory should tell us we should get that one here. So if that is 0.1 here, we get, so to say, this is 0.1, 0.2, 0.3, 0.4, 0.5, and so on. So there is a fairly good fit, we believe, and that was recently published in a PRL paper. Interesting enough, these factors here that appear here, the group theory can also tell us something about it. And it actually tells us under some kind of weak assumption that this is an exponential law. And we just took the data from the DNS, and this is, so to say, the black and the dashed dotted line here is from the theory, and the dots here, the crosses and the stars are from the DNS. And that gives, I think, a reasonable good fit. Well, now let's go to the experimental data. We also looked at some experimental data. I'm not showing all of them. There's an enormous amount of data. This here again, I think this is the superpipe experiment. We see the log. Depending on the Reynolds number, of course, the log is longer or shorter, as you know. Then here, this is the higher moments. Also, this is the Cyclope 1 experiment. It looks very, very close to the theory. Numbers are similar, slightly higher omega of 0.11 instead of 0.1 that we saw in the DNS. This is this indicator plot. So the flat regions here, so to say, show that this is supposed to be valid. And also this exponential behavior in the free factors that the group theory told us is observed here in the experimental data. Now let's move on to the second region that we looked at, and that is the center region here. That's essentially the center part of the channel and also the pipe flow, that what we call deficit region. And here essentially we really don't know what is symmetry breaking, so we left that open. And if you do so, you can guess that you get the power law. That is what we actually putting forward. In fact, I already proposed this one here in 2000 or 2001 in a JFN paper. And what we see here is that they are all power laws. So they say this for the deficit law of the second moment. And for the nth moment, we find the following here. So there is a factor of n here. This is the second and the first one here coming from the second, first and second, and also that one here. So that is what the symmetry theory tells us. And then we started to compare that to some of the older DNS data. And what we see is that we shifted all the curves here in order to better see. So this type of deficit lot seems to be very insensitive to Reynolds numbers. So this is 2,000, 4,000, and up to the 10,000, our DNS here. What is interesting, however, is that these two sigmas here are the same, almost the same. So this is just the first and the second moment. Now this is from our DNS, and this is the first, the second, the fourth, up to the sixth moment. And what we observed, in fact, is that these sigmas here are exactly almost the same. That means there is no type of dimensional scaling here. This is almost zero here. So we only have this remaining part here. That is, if you compare it, just a constant. That means this is kind of a strongly intermittent behavior. If there is no power law type of scaling behavior visible, that is what we usually call intermittent scaling. Also here, these prefactors can be computed. It's exponential. Also that here is from the DNS data. And one can actually see something similar also in the experimental data. That is the pipe flow, the center of the pipe flow, also deficit scaling here. Numbers are quite similar, even though geometry is quite different. Also this exponential behavior of the prefactor is also visible here in the data of the experiments. Okay, I guess I'm getting toward the end. I have a few more slides. What we did recently, there were some criticisms on this H moment scaling behavior. So what we did is we looked at scaling behavior of U2 and U3. So far, you just saw the scaling behavior of U1. That is what people usually do. Well, the argument was that the mean velocity dominates this H moments, which definitely is true. So to leading order, if you look at the H motor and expand that in terms of, so to say, the mean velocity and the R moments, then you find something of that sort. So the question is, are they really true or not true scaling laws? So for that reason, we looked at the U2 and U3 moments in the center region where we have this power law scaling. And if you just look at it, you can recognize easily in the theory that the behavior should be almost the same. However, the major difference is in the 2 velocity, that is the wall normal velocity, and the U3 is the span-wise velocity. The channel flow has no mean velocity part. However, one has to be careful. U2 and U3 moments converge much worse because they don't have this mean, because the mean is missing. And also the odd moments converge extremely poor. That has to do with the PDF and the multiplication of that in the odd moments. And in fact, for U3, you can formally show that these odd moments are exactly 0. So what we do, we just compare the 2nd, the 4th, and the 6th moment from our data. And that is what we're showing here. So this is the moment, the 2nd, the 4th, the 6th moment. You see quite some fluctuations here because we're just going to start a new simulation because we want to have much better statistics here on these V and W moments. However, the curve that we're doing here, the black lines, are due to numbers that came from the U1 component. So that is the sigma 1. The sigma 2 came from the U1 moments. And that seems to be very close to what we observe also here for the V, I mean the two U2 and the U3 moments in terms of this deficit type of scaling. A second thing was how good is the H moment scaling for Reynolds stresses, right? I mean, we just looked at the moments, and here we played with that, and specifically we look here at the near wall scaling. So of course the Reynolds stress, the U1 stress, is simply the second instantaneous moment minus the mean velocity squared. We had to do some minor adjustment of the parameters, and still, I mean, those who have actually looked at other people's work, we can actually get a very good fit to the stresses here in the region where we believe things are hold true between around 200 or 300 up to around 3000. That is, I think, visible here. The PDF scaling behavior is still under construction. I would say, no, the theory is finished. So completely analogous to the moment scaling laws, a PDF scaling law can be derived from these aforementioned statistical symmetries. So that was derived as part of a PhD thesis in my group. He also showed, that is important, taking the nth moment, he could recover exactly all the scaling laws that you saw earlier. That means this near wall behavior, log region, depends on very much on the numbers here, of course, and also this deficit scaling. With that, I guess I'm coming to an end. So I think the basis for what we've seen today is this H moment equations. Most important, it's a conservation law. I think it makes sense to look at conservation laws other than the classical behavior. Sets of statistical symmetries have been derived. They're kind of hidden in Navier-Stokes. I've discussed it quite a bit with some mathematicians, but still things are unclear, I would say statistical symmetries mirror key properties of turbulence, things like intermittency and non-Gaussianity. The key ingredients of classical and higher moments, for example, you cannot get the log law as a solution to the moments if you don't have a statistical symmetry. Statistical symmetry give rise to anomalous scaling, and in particular, scaling laws are invariant solutions to this invariant infinite set of moment equation, also the PDF. Scaling laws can be derived rigorously from symmetries, and well, as you have seen, scaling laws are particularly simple in this H formulation because it's a conservation law. Well, you can write down everything in the R formulation, and the however that will be probably. Oh, I'm sorry. Okay, thank you all for listening. It was a pleasure being here today. I will be at the Isaac Newton Institute beginning on Sunday, as you probably all heard. So I will be there the entire week next week. So I'm happy to take more questions. Thanks a lot.
Questions? Right. Yeah.
So thanks, Martin. Can you just go back? You said that that additive symmetry is not Galilean symmetry. Why not?
Hold on. Oh, you might. Yeah. Let me just go there. Yeah, I know what you mean. This one here. Yeah, exactly. Well,
right.
It seems to be Galilean invariance. That's right. However, if you look at the moment equations, put it that way, in order to show formally Galilean invariance, for example, in Navier-Stokes equation, you need to have the unsteady term. You need, so to say, the moving coordinate system, and then you add this constant here, and then you see Galilean. For that, you need the unsteady term. So, however, for the flows we're looking at here, they are statistically steady, so there is no unsteady term. So you cannot formally prove Galilean invariance on this very reduced set of moment equations. That is just not doable. It just doesn't work. I mean, if you just put it in there, it fails. I mean, that is the reason.
X2 star is equal to X2, and X2 plus T. The X2 star is so you want one example first.
Follow-ups?
Well, it's the first one.
Yeah, there's no assumption.
I'm not sure. I hear some mumbling. I'm sorry, but
we're trying to work it out.
We're discussing.
Yeah. There's more questions. Don't worry.
You're telling me I'm wrong.
Yeah.
So, thanks, Martin, for nice talk. I just wonder, actually, this symmetry transformation you introduced should be applicable to other flows, right? So why is it? I don't know whether you have applied those things to other flow to get the scaling from the other flow. For example, that's one question. The other is that this will be useful for bounded flow. I don't know. So just because I didn't know these approaches at all, so I was just curious because it seems that it could be applicable to like free shear flow, for example.
Yeah, I mean, the symmetries are kind of building blocks. I mean, you can apply it to a variety of flows. I mean, apparently you cannot apply it to an engine or an airplane. That would not work. But what we're doing right now is I have a larger jet DNS, so we look at jets and higher moments in jets. We did a variety of other wall parallel flows or wall bounded flows, for example, in rotating frame and these kind of things. So that's doable. Yeah, that seems to work reasonably well in a large variety of different flows. Yeah. In fact, I just started to also look at homogeneous isotropic turbulence. In fact, where people have speculated a lot on this anomalous scaling, and that there's this deviation of the power law behavior that was proposed by Kolmogorov, and what we already see is both in the PDF equation but also in the moment equations that there is many more statistical symmetries. So there is at least some vague hope that we get some understanding from a symmetry point of view on this Kolmogorov type of behavior for higher moments. But that is a few years down the road, I would say. But things are already visible that more statistical symmetries exist if, so to say, if you impose, so to say, statistical isotropy, for example, then things pop up, so to say, naturally.
Can I just follow up on that? Martin, what, in terms of the physics you've actually got in your symmetries, it's translation invariance and then translation in function space and then simple scaling. I mean, presumably it would also hold for 2D boundary turbulence, like channel flow, and then you predict the same log. Is that correct?
In 2D?
Yeah.
Oh, that's it. Oh, you mean if you would do a 2D simulation?
Yeah.
And compare that?
Well, no, I mean, like, would you predict a log left 2D channel flow?
Good question. I don't know.
I mean, it seems to me that what you're doing is you're finding scale invariant profiles away from boundaries, but you don't know whether they're going to be realized or not.
True.
It is
True.
in 3D, but it's not in 2D. Is that correct?
I fully agree. So the thing is that we are able, so to say, to construct invariant solutions even for arbitrary moment order. However, yes, we have not solved the turbulence problem, definitely not, because we cannot solve, so to say, the whole moment system between the two walls. I mean, we're just looking at regions, and
Yeah.
we have to kind of patch the regions, and we have to compare the data. That's for sure. Yeah. No, I mean, what we do is really we construct solutions and ask the questions, and symmetries actually help us. Where they might apply. Yeah, that's true.
Yeah, so here actually, when I look at the transformation, you have e to the a s x, those minus or a s t, those actually a's. Are they determined from the data, right?
Yeah. We have, I mean, I have an idea how one might be able to formulate based on the PDF actually and some kind of an eigenvalue problem for these parameters, but also this is some years down the road. I know how to formulate, but it's kind of not so easy. So I mean, as you say, I mean, turbulence seems to pick, if you believe what I've shown you, or if you believe in the log law. I mean, say, where is it? Here, what picks kappa? Yeah, that's unknown. Or what picks the B? Say, well, as I said, I believe at least in the PDF formulation we might be able to formulate an eigenvalue problem. Yeah. But we have to see if that works out.
Yeah, so I'm trying to understand more at the rigorous level, because the idea of the groups, etc., is more something supposed to be invariant globally, etc. Yet you are applying it locally. Am I correct in some sense? Like basically say, okay, they are supposed to be global if I don't have boundaries. So let me now focus what's happening locally. Is that correct?
Yeah, exactly.
And from looking at the transparency that you are sharing, I don't see any elements other than scaling in some sense in the groups. Is there anything other than scalings that, other than the groups? I mean, like,
well, say this one here, for example, that was the shift in the, where is it? Give me a second. The shift here in the velocity and also in the moments. That appears here again, and also that appears here. If you don't have that, that is a statistical symmetry. If you don't have that, you won't get the log. No way. There's no way to get that. I mean, so that I think is the answer. No, scaling is not sufficient. No, you have to have more symmetries.
Wait, is that true? I mean, do you need A1H? I mean, when you go to solving U1, you don't need U1N or H.
No, that's right, but you need that one here. That is true. I mean, what You don't need that one here. That is for the higher moments, but you need that one here, and that is a statistical symmetry.
Why do you need that one?
Excuse me?
Why do you need A1H?
Oh, because if you remember that for the log, I mean, this one here is 0, right? I mean, that is essentially this one here. So if that is 0 and that is 0, then everything is 0 here. Then you don't get a log. So you need that term, that constant here, to get a log law.
So what does that mean? Because if I'm not considering H's, what does that symmetry actually mean? A1H.
Oh, that means it means kind of well, it means that you can add. Let me just go back. You can just add something to the velocity.
Because I mean, these are separate, aren't they? A, I, N. I could set those to 0.
Yeah, you can set that to 0. Then, well, that does not affect this one here. Yeah.
So so it means I'm keeping X2 fixed, and I'm changing the mean profile by a constant. Is that what it means?
Yeah, exactly.
So it's,
in fact, this is also important. I mean, if you let's go to that one here, to the second scaling behavior here, that one. It also appears here. Now, oops. It appears here and also appears there. Now, I skipped, of course, some calculations. However, where it appears then, in this constant part here, in this deficit part, this constant, that this A1H or H2H appears here and there. So yeah, that is needed.
just in log layer.
Excuse me?
Just in terms of the log layer, I just need A1H, don't I?
Yeah, for the log layer, you need that, definitely.
And it's just, isn't it Galilean invariance? I'm sort of coming down on the side of Dwight.
Excuse me, I don't get that acoustically.
I'm allowed to view the velocity, and I could be moving in a different frame to the flow. Maybe I'm in a speed bump, I don't know. And the velocity I measure is going to be, I mean, is it a constant?
Yeah.
It is a constant, yeah, kind of. I mean, it's essentially U tau, I would say. Call it U tau here. I mean, this is essentially a constant, or this one over that one is U tau, or U tau over kappa.
You don't need H. You don't need your statistical perspective, do you, to get the log layer? I mean, it's just scale invariance.
No, that's not sufficient. You won't. As I said, I mean, so let's go to the log. I mean, for the log, you want this one to be 0.
Yeah.
No, and now if that is 0 and that is 0, this equation.
No, we keep that.
Oh, you want to keep that?
Yeah, I like that too.
Yeah, okay.
Yeah, because it's it stops it trivializing. But
Well, that's how you're gonna get the log.
So my statement is just if you don't have this statistical symmetry here, you don't get the log.
But it's Galilean invariance, isn't it? I mean, you saw.
Well,
You
the point is, if you try to show, as I said before, if you want to show that this is Galilean invariance, it will not work in the moment equations because you're missing most of the term that you need for Galilean invariance.
No, but can we ask it this way? I mean, this does not imply Galilean invariance, but Galilean invariance implies this, no?
Well, that's a question. Yeah, I mean, as I said earlier, I mean, in my first paper that was in the 2001 JFM, I was saying this is Galilean invariance. I don't believe that anymore, but because then, well, what does that moment here, and also that of the higher moments? So, well, that is to be debated. Yeah, I mean, one might say that is Galilean invariance, so it is induced by Galilean invariance.
That's right, yeah.
Question, yeah.
That is to be discussed. Yeah, I mean.
Yeah.
Yeah, thanks, Martin. Really interesting talk. Just trying to understand, apply the symmetry breaking. So you say, you do that, so you choose that to be 0, that breaks the symmetry, but you do it at a specific wall location x2. So how does, I'm just wondering how the Reynolds number comes into this. and deciding at what point away from the surface you can apply symmetry breaking and where you can't.
That is something that I cannot tell. I mean, the symmetry breaking essentially is, it seems to be a local effect, I would say, because here apparently, because the mean velocity is, so to say, determined by u tau, as we know, and it scales with u tau. I mean, that is what the Cameron and Prunsel found. So there is no freedom in terms of these parameters here to scale that.
Now, why can't I apply it then closer to the wall, say in the sublayer?
The reason is that, and that is what probably goes also to your second question, that is Reynolds number dependence. Let me go back to what I showed here. Give me one. No, hold on.
So the scalings depend on basically Reynolds number going to infinity. Is that?
Yeah, exactly. That is exactly the point.
Right, and so that's a strong assumption. So you're talking essentially going to asymptotic Reynolds numbers.
Exactly. That is. This assumption is definitely not true for small scales in terms of Kolmogorov length scale, and is not true near the wall, where, so to say, we have a major influence of Reynolds numbers. So yes, that's true. This is a strong assumption that does not hold very close to the wall, say, in a certain region, and it does not hold for small scales in the order of Kolmogorov. Yes.
The other way, if I keep going away from the wall, that assumption becomes better. In other words, there's less chance of viscous effects.
Yeah.
Yet you can't apply the same symmetry breaking. I'm not sure why. Why you can't use that same argument away from the wall as you get to the edges of the answer.
Sorry, the last part I didn't understand. Sorry.
Yeah, so I mean, I'm just trying to follow the logic. Why
Yeah.
in the wake region, why is the symmetry breaking doesn't apply there? Because that viscid condition is stronger, it's closer to being right.
Let me just go back to that one here. I'm not sure I fully understand the questions. The question, I mean, the tau, the tau wall, of course, is not only valid, so to say, in the near wall region, but also is apparently a constant in the log region, right? However, in the log region, viscous effects are negligible. So then this u tau quantity becomes a dominant parameter. I would try to physically argue that way. Not sure if that is convincing.
Martin, I think you're getting quite a few customers for a nice Blackboard session when you're here next week.
Yeah.
Any other questions? Okay, I think we're finished here. Thanks very much, Martin, for a very thoughtful.
Okay, thank you very much all. Thanks for listening, and I hope to see you all next week. As I said, I come on Sunday evening, Sunday afternoon. Take care. Bye-bye.
Thank you very much.